welcome to the meeting tonight. We're here for our August 16th meeting. You've already read that. If you have a badge tonight or you bought a badge tonight, be sure to get a raffle ticket. There's someone in the back there with raffle tickets if you need one. So anyway, I'm going to try to speak because this new mic is kind of interesting as well. It kind of comes in and out, seems like. All right, let's get going here and see what we see. All right. I think we're good to go here. All right. As always, welcome everybody. For those everybody in the room, everybody on Zoom. Hopefully the folks on Zoom can hear. We're not sure, but we thank you for being here with us tonight. As always, I say this every week. We hope you enjoy yourself. Number one. We hope you learn something interesting. Number two, we hope you make a new friend. Some of you have never met before from the club, and then we hope you reconnect with some of your old friends here at the club. So welcome and good evening, everybody. This is the time when you pull out your cell phone. If you didn't remember to put it on stun and get your cell phone on stun. I've actually done that a few times myself. In fact, there's been a couple of meetings I've been up here leading. I'm thinking, oh my gosh, I didn't put my phone on vibrate.
Just gotta stay near the laptop.
Okay. Oh, they're picking it up off the laptop. Okay. Well, apparently they can hear, but it's through the laptop. So I'm kind of glued here. Can you see me now? No. Okay. So anyway, next thing up, any visitors here tonight? Anybody new here tonight? If so, raise your hand. We'd like to at least say hi to you. And if we have anybody, but what? He's got it. We have one new visitor tonight. So. Well, welcome. We're glad to have you here tonight. Anybody else? Anybody else here? Oh, we got one more over here. So, hang on.
Friends and glad I love here.
Okay, well, welcome. Glad to have you here as well. Anybody else? We have twos. Any third? Do I have a third? Do I have a third? Going? No. All right. Thank you for being here tonight. We appreciate having visitors all the time. So anyway, tonight's agenda, as you can see here, we have our standard 5 to 6 minutes of announcements coming up here in just a moment. We do have a special recognition tonight. Look around. Is Marty? Are you in the room somewhere? Oh, there we go. All right, perfect. So I just said, didn't see you, and I just wanted to make sure you're here, Marty. So welcome. Let's see, star parties. We got a couple of star parties coming up that we're going to mention a few things about that. We do have a raffle coming up after that. And then we do have one member presentation tonight from Ted Blank, and you can see the title of it there. And then we've got our 7th inning stretch. We take like a 10-15 minute break, let everybody mingle, get a snack, get something to drink, whatever. And then we'll have our main presentation from Amy Zhao here tonight from ASU. And Amy's just sitting right over there, and we'll all get to meet her in just a little bit. So anyway, so this is tonight's agenda. Let's just go ahead and get to it. We're starting the standard 5 to 6 minutes announcements we do every week. So general announcements, for those that are here all the time, you could probably do these slides for me at this point. So anyway, if you want to join or renew a membership, remember, there's 3 ways to do that. Number one, you can see Brooks at the back table back there, and he can set you up right here, right now, tonight. But also out there on our website, the East Valley Astronomy Club website. You can also do it online and make your payment via PayPal, or you can do it through the mail and just mail us a check. So there's at least 3 different ways to join. Once you join, notice there is a new member guide button up there. And that tells you kind of what membership involves or whatever else. If you click on that, it just brings up a little PDF. And you can read that PDF and kind of see what it means to be a new member. So if you click that new member guide button. If you want to know what's happening here at EVAC, there's at least 4 different ways you can figure that out. Number one, you can join our email distribution list. So you go out to our website, you click on that subscribe button you see there. You end up on the EVAC announce at freelist.org distribution list. And you'll get probably 6 to 8 emails probably a month out of that alias, that email distribution list. And anything that's coming up, we typically announce it out there, so you see it. We do not, sell email addresses off to other companies and all that stuff. You're not going to get a bunch of spam from other places, but gives us a way to communicate with you through that email alias. We also have out on our website a news and, an events and meetings link. And there's a calendar there every month, and it shows you what's happening at the club on that calendar. You can click on any of the events list on that calendar. It brings up details of what's happening. So that's available to you as well. Also, we have a newsletter that we put out every month, and it has what's happening on the newsletter as well, a couple of other articles, and then it actually tells you what's happening in the sky that month as well. Bill Dellinges and James Yoder and a few people put articles in that newsletter saying, hey, these are the things you can look for in the sky that month if you're so inclined. So the newsletter is actually a good thing. All newsletters are archived, so you can actually look back at past newsletters as well. And we archived several years of those, so those are available to you. And then the last way is we have a Facebook page as well. You can join our Facebook group, the East Valley Astronomy Club Facebook page. We have about 1,000 people now that belong to that Facebook page, and you'll see all sorts of stuff there because, it's just like any other Facebook group or Facebook page. People post whatever, oh, here's some shots of what I did last Friday night out at Picket Post or whatever it might be. So the Facebook is a really good way to stay sort of connected as well to other members in the club. If you do not have a telescope, if your boyfriend just hasn't bought you a telescope in the last couple of weeks, if you need a telescope, there's a couple of different ways to do that. We do have used equipment coming in all the time. James Yoder, who's not here tonight, he's off vacationing in Durango, Colorado right now. He takes a look at all the scopes, refurbishes them, fixes them up as necessary, and then we make those available at a very much reduced price. And so sometimes it's a little push-to scope, sometimes it's a full go-to scope with computer drives and all that. So it always varies because all sorts of stuff's always coming in. We also have equipment for rent, very, very minimal price for equipment for rent. Once again, we have push-to scopes, we've got go-to scopes. We have one of those new ZWO C-Star units now you can rent. That are so popular, that new electronic scope. And we also have like an astro photographer setup as well. So if you wanted to try astrophotography but don't have a few thousand extra laying around for it, you can rent a kit from us. It isn't really set up for deep space objects, but it is set up for planetary type astrophotography. So you can rent that kit for a few weeks and get a feel for it and say, yeah, I want to start saving up some bucks. I want to get into this. This looks like fun. So that's going to be available to you as well. If you'd like to learn more about the hobby or specific technical things, whatever else, also on our webpage, we have a virtual beginners lab, as you can see there. Each one of those blue boxes brings up a section of text that discusses whatever that topic is. You can't see them all, but there's 33 boxes there on that screen, and you can click on any of them and read a little bit more about what's happening or how something works or whatever. So that's available to you also. And I think it's just the last of the announcements. One of our charters as a club is to give back to the community. And so there's a couple primary ways to do that. Number one is to get involved with as a telescope operator at our observatory. So most of you are aware, but we have a few visitors in the room tonight. We have an observatory about a 5-minute walk that direction. And as you can see there, you can sign up and become a volunteer telescope operator on Fridays or Saturdays nights, clouds permitting, of course. The nice thing about that opportunity is that you have complete control over your schedule. What'll happen is every month, towards the end of the month, Claude, who runs the observatory, will send out an email saying who's available this month. And you can say, I am or I am not. And let's say you plan on being on vacation for 3 weeks, you're just not around. You can say, I'm not available. He won't schedule you. Or you can say, I'm around, but I can't work this Friday or that Saturday. You've got tickets for the ball game, you got tickets for a concert, whatever. You can pick and choose when you're available and when you're not, and then just volunteer one night for the observatory. The good news is that by next month, it should be a lot cooler. All of us who've been volunteering over the summer are glad to see the summer heat abating because observatory is hot. So anyway, I think I'd rather be cold with a jacket than just standing there sweating. So anyway, but it's a fun thing to do on fall, winter type nights when the nights are longer. We often have pushing 200 guests come through the observatory. So it's quite busy. So it's quite nice. During the hot summer months, we're good with about 50 people usually. Not too many people are wandering the park on these hot nights. The other thing we have available if you want to get involved is these private star parties, essentially nearby events that we sign up for at HOAs, schools, science centers, whatever. And we go out with a handful of people with a handful of telescopes we set up, and the people look through our telescopes. And it's a lot of fun. A matter of fact, that'll get really busy here starting next month because we are cooling down. The monsoon clouds will start to finally dissipate. We'll have a little bit clearer skies finally. The temperatures will be under 100, so we'll have a lot more star parties. Plus, it'll get darker earlier. It's hard to have a star party when it doesn't get dark till 8:45. But once it starts being dark by 7:15, it's a little easier to have star parties at that point. So anyway, this will be big. In fact, our events coordinator will be pretty busy here over the next 6 months or so now. If you're happy to have this club, there's a whole list of people that work on our behalf to make this happen for us. So I've listed them there. A few of these, like Woody is out on vacation. He's in Eugene, Oregon. James Yoder is out once again. He's in Durango, Colorado right now. You'll see everybody listed there. And then as always, we have the board members there listed at the bottom that help provide direction for the club. In fact, the raffle that we're having a little bit later this evening was something that came out of the board meeting earlier this week. So, so the board's always involved with things. Notice that Morgan Moran's name up there is in red. So you might wonder, well, why is that so? And it's mostly because I just don't like him. No, that's not true. I like Morgan a lot. So anyway, Morgan, you here tonight? Did I see Morgan? Ah, there we go. You're in the back. Oh, you're hiding from me. Glasses and hat. I would have never recognized you. So anyway, Morgan, this was his first month publishing the newsletter. So I wanted to call that out. He volunteered last month to start taking over the newsletter. And so we're happy to have Morgan taking care of that. He's also one of our board members also. So I think you're going to try to do it all on your own next month. This month he worked with Marty, who was our previous newsletter editor. But Morgan, I guess, is going to try to do it all on his own on next month. Which then brings me to this. Special thanks to a special volunteer. I mentioned Marty just moments ago is turned over the newsletter editing to Marty. And I want to call out, or over to Morgan, but Marty, I wanted to call him out. Marty Paisonk has just retired as our newsletter editor. He's still going to sort of hang around in an advisory role for a time to make sure Morgan's got good footing underneath him. But Marty is a special volunteer. We wanted to recognize that. Here's why. He's been the club's newsletter editor for 11 years now. So that is a long time to volunteer for something. That's just amazing. Oh, it gets better. It gets better. And those are contiguous years, not off and on years. So like a lot of people, they might be president for a year or two or the secretary for a year or two, but then they get a break. Marty's been doing this for 11 years. If you thought 11 years was big, look at this. He was also the club's webmaster from 2004 to 2023. So 19 years he did the webmasters. So that's special. So we really want to thank Marty. And as a result, on behalf of the club, Marty, we'd like to thank you for everything you've done for the club. And as a matter of fact, we have a little gift. So Morgan, 18 years from now, so anyhow, you're all set. All right, so thank you so much, Marty. We appreciate all that you've done for the club over the years. Star party time. We actually have some star parties coming up. One you might know of, and one that just came up in the last week or so that we discussed in the board meeting last Monday night. So let's talk about this. So quick reminder about our upcoming All AZ Star Party. When is it? If you paid attention, you know it's coming up very soon. It's November 1st and 2nd. That's a Friday and a Saturday. So start blocking off the date to join us for our All AZ Star Party. Where it's at the normal place we always go. It's out at the Hovatter observing site off of the west I-10 on your way out towards like Quartzsite. And you can arrive anytime on Friday. Actually, you can arrive earlier, but we won't be there till Friday sometime, and then we'll pack up Sunday morning and typically go home. Who's invited? Everybody. Bring one, bring all. The more we have, the better. When we had the last event out there, the Saguaro Club joined us, and we had over 100 telescopes set up. It was a lot of fun. That was a lot of people out there, and it's a huge area, and so it fits 100 people easy. You could probably put 250 people out there. Anyway, please join. It's a lot of fun. And the club does provide dinner on Saturday night. So you're kind of on your own for Friday to eat on your own or, whatever. But on Saturday night, the club does have sort of a big group dinner out there. And I get to try chefing again this time around. So, and also we have raffle prizes. I've already started working on that. I've been contacting various companies and stuff around the valley trying to get some raffle prizes. I've got some commitments already. And so bring your folding money and buy some raffle tickets because typically we end up being able to raffle off some really, really nice things. So hopefully we'll have nice things again this year. Now that happens every year. The All AZ Star Party happens every year. But just in this last week or so, we've had another opportunity arise, so we're going to introduce it tonight. We don't have a lot of details yet, but we'll give you details very shortly because this is coming up soon. There is this place up on the Mogollon Rim called the Hyman Rim Ranch, okay? And we have been offered that property to have a star party if we want to so do that. So James Yoder, who normally sits right here, but is not here tonight, he's going to organize it. Him and I spoke like 2 nights ago on the phone, and he's going to contact the owner of Hyman Rim Ranch, a guy named Jerry Hyman, who would have guessed, huh? Anyway, he's going to talk to Jerry and set up a date. I think we're shooting for the first weekend of October. So it's about 4 weeks before the All AZ Star Party. And here's some of the details. You can kind of glance through that list of bullet items I just showed you. Essentially, he's got a wonderful property up there. He has about 100 people in his extended family. He's built this giant, like, sort of camp resort for his whole family. And so he's got an archery range up there and a gun range up there. And he's in the process of planning to put a trout pond up there so they can fish. And he's just got a little bit of everything. And he's offered that to us. And so James is going to try to set up something tentatively for the first weekend in October. And one of the things he has up there is he's graded off a 50 by 50 foot level pad for telescopes out away from the trees. And so if everybody gets like a 10 by 10 area, it would accommodate about 25 telescopes. So we will be seeing email from James about that probably in about a week. And he'll start seeing who might be interested in going up to the rim. We're thinking about maybe doing a Thursday, Friday, Saturday. You could come 1 night, 2 nights, all 3 nights. It's up to you, but that's kind of what we're thinking about setting up. Anyway, we'll have more details about it and what it's all going to be, like I said, in about a week. But this just became available to us, and a couple things here. There's just a couple pictures. It is Bortle 2 skies up there. So he says on a good night, you just look up and you can actually just look at the Andromeda galaxy. It's just right there. You actually see it bare eyes. So Bortle 2 skies, it's got a couple of bathrooms with, sink, toilet, shower, that sort of stuff. There's water on site, power on site, big pavilion, big covered pavilion with room for 100 underneath of it. So it looks like a nice facility. So we're going to try it out and see how it works. So anyway, so stay tuned to your email. It will go out in email, probably Facebook as well. And if you're interested in maybe doing this 4 weeks before the All AZ party, you'll have that opportunity to do that as well. So anyway, some nice things up there. I talked to Jerry actually 2 nights ago for about half an hour. Wonderful man. I wish I could go up in October myself, but I already have travel plans. So I'm not able to do it, but nice guy. I'd love to go up and see his facility. Anyway, we are at raffle time. So here's the thing with the raffle. We had a board meeting on Monday night, and we, as a club, we have certain, expenses we have to cover every year. You'd be surprised. This is my first stint as president. I had no idea all the insurances we had to cover and carry, and we have to pay certain things for the Hoveder site, and there's just a lot of expenses. So your dues pay for a great deal of that as a club member. So we thank you as members for paying your membership dues every year because it helps keep the club running and pay for all these things you need to pay for. You like cookies and Cokes and sodas? That's all paid for with your dues back there as well. So anyway, turns out that this year we are doing financially pretty well. And so we thought, the board thought, what a better way than to maybe give back a little bit to the membership here. So what we decided to do is raffle off. Everybody likes money. Everybody likes Amazon. So we have two $25 Amazon gift cards here, and we're going to raffle them off right now. I have a ticket too, but if I win, I'll give it to somebody else because I don't want it to look like it's rigged. So anyway, we've all seen that. So anyway, and let's pick one in here. I'm looking this way, and oh, you won. No, I'm kidding. So anyway, all right. So let's see. Here we go. So first number is 082, and last three numbers are 099. Oh, you're going to decline? Okay, we'll pick another number. Better not be Tom next. So anyway. All right, so here's first three again, 082. Oh, we went from 099, we went down to 088. Oh, there we go. So anyway. There you go, Bob. Okay, so anyway, by the way, we are going to do this the rest of the year, and then our first board meeting in early January, we'll decide where we are financially. We may continue, we may not, but this is sort of the plan for the next four or five meetings anyway. All right, let me pick another one here. All right, same three numbers again, 082, and the last three are 096. Ah, there we go. Yeah, I like giving money away. That's fun. So anyway, we should do this every month. All right. Thank you for your help there. Appreciate that. All right, that was it for the raffle. So we do have a member presentation tonight before we go to our first break and then get on to our main presentation. Tonight's presentation is from Ted Blank. You can see the title there, and Ted's on his way up here. And I apparently this works for the room, and mine is for Zoom. So you got to sort of stuck here. Just down arrow, and you're ready to go.
Thank you, Steve.
Okay.
Hi, everybody. Good evening. My name's Ted. I live in Fountain Hills, and you might know we're in the middle of construction of the International Dark Sky Discovery Center up in Fountain Hills. It broke ground last month, so we're pretty excited about that. Ask me if you have questions about that. But tonight I'm going to talk about a little expedition that I took last month, actually just a week ago. Tonight is Trojan asteroid night, if you hadn't noticed from the list of speakers tonight. And this was an expedition sponsored by the mission, the Lucy mission, paid for by the Lucy mission and operated by the Southwest Research Institute. They're based out of Denver and Boulder, Colorado. And their mission is to support the Lucy mission by doing these things called occultations to determine where the asteroids are that are the targets of the Lucy mission. It turns out there's no more accurate way to find out the location and orbit of a solar system body than to time the time at which it occults or blocks the light from a distant star. That's a very, very accurate way to determine its location. And that really helps when you're trying to steer a spacecraft to encounter this object and don't particularly want to run into it. So occultations are the method that Southwest Research Institute uses, and they ask lots of volunteers to come and help operate their equipment, go out into the field, be in the right place at the right time, and operate the equipment to record these events. The data reduction then goes right back to the Lucy mission specialists who use it to target the various objects that they're heading for. The mission last week was to study a binary asteroid called Patroclus and its partner Menuetius. They're huge asteroids, many miles across, and they are part of what's called the Trojan asteroid swarm. The Trojan asteroids are asteroids that share Jupiter's orbit at two Lagrange points, 60 degrees ahead of and behind the planet Jupiter. So they found a safe place to survive for billions of years without being consumed by Jupiter's gravity, like lots of other main belt asteroids that get thrown out into space and Jupiter sucks them in and they disappear. These asteroids are very old and they're representative of the ones that helped form the solar system. So they're of great interest. And the Lucy mission, which was launched last year, is on its way out to the Trojan asteroid belts on a 6-year mission to study 8 different Trojan asteroids. The Trojan asteroids are not part of the main asteroid belt. You're probably all familiar with some of the larger asteroids like Ceres and Vesta. The main asteroid belt occupies that big gap between Jupiter, Mars, and Jupiter orbits. But the Trojan asteroids are out actually sharing the orbit with Jupiter. Back on November of last year, the Lucy mission encountered its first target, a small asteroid called Dinkinesh. And I believe our main speaker tonight is going to talk a little bit about that. So I won't steal her thunder at all. But what we were doing was investigating the location and orbital parameters of the very last Trojan asteroid that the Lucy mission is going to investigate in just 8 years and 198 days from now. So it's on its way out, and the actual orbital parameters of this mission involve 3 Earth flybys after going out to the Jupiter Trojan area and then coming back to Earth to alter the orbit to cross the solar system to the other side. I don't have time to show you the animation of the entire orbital parameter, but if you look up in the upper left corner, you can see the path of the mission. It involves going around Earth 3 times. David and Joan Dunham are here in the audience, and David spent his life calculating trajectories like this for spacecraft. So if you want to know how to get home tonight, either with the least amount of gas or the least amount of time, David's the guy to talk to. You can see pointers on this chart to the Lucy targets. They're all out in the true targets are out in the Trojan asteroid belt, but there are 2 main belt asteroids that are kind of test objects. One of them is Dinkinesh, which was already encountered, and the other one is an asteroid called Donald Johanson that'll be encountered next year. Then they'll test all the equipment on both of those asteroids to be ready for the flybys out in the Trojan swarms. This business called occultations, it's kind of like an eclipse. It's when one object blocks the light from something behind it. And in this case, what we do is we put observers out into the field at different places along the shadow that the asteroid would cast on Earth. Try to imagine a single star, millions of light years away, is casting a shadow of an asteroid on the planet Earth. And as the asteroid moves across the solar system, the shadow of the asteroid crosses the planet Earth. And because the star is so far away, the shadow of the asteroid on Earth is exactly the same as the sky plane projection of the asteroid in the sky. Same shape, same size, whatever position the asteroid happens to be in at that time. So by positioning multiple observers across the shadow, we can measure the diameter of the asteroid at different locations on its body, basically by seeing the star pass behind it at different places. So in this example, we've got 5 observers on Earth. The shadow is passing across them. The asteroid shadow is big enough to block the starlight from observers B, C, and D locations. But observers A and E are outside the shadow, so they don't see the star disappear. And what we do is time the moment at which the star disappears and the star reappears. Those 2 pieces of information, along with your latitude, longitude, and elevation, provides all the information the scientists need then to calculate the position and improve the orbital knowledge of the asteroid itself. And that's helpful. There were several occultation opportunities for Trojan asteroids whose shadow actually crossed the Phoenix Valley. And back in May of this year, David and several other people participated in an occultation campaign where several positive occultations were noted. And you can see that the shadow of this particular object went right across the Phoenix area. It didn't take too much driving to set up a telescope out in the field. And we had 3 positive occultations and 2 misses. The blue lines there represent the edges of where the asteroid shadow was predicted to be. The red lines outside of those represent the 1 sigma error bar. So basically that shadow should be somewhere between those 2 red lines about 2/3 of the time. That particular set of data was very interesting because there's a group in Czechoslovakia that uses light curve analysis to determine what convex shape of an asteroid could give a particular light curve by monitoring the reflections off the asteroid as it spins, and the light gets brighter and dimmer as the various portions of the asteroid reflect sunlight towards Earth. If you monitor that light curve long enough, you can do an inverse calculation and say what shape of an asteroid could possibly give rise to that light curve over an 8 or 10 hour time frame. And this was the prediction that they made. But when we connected the dots of our occultation results, we actually got a shape that looks like this. So this information is fed back to the modelers to say, if you had multiple possible shapes for the asteroid, the one that you published is probably not the right one. Go back to your data, check it again. And they really appreciate that because many times there are multiple convex shapes of an asteroid that could give rise to the same light curve. And our data allows them to determine which ones of those shapes are actually the ones that are consistent with the light curve data that they have achieved. So back to our mission. The Southwest Research Institute has been doing this kind of support for missions all the way back to the New Horizons mission that went to Pluto. You might remember that after New Horizons went past Pluto, there was an opportunity to visit a Kuiper Belt object. And there were several candidates. They had enough fuel to divert their trajectory to them, but nobody knew exactly where they were. And that was very important because it's very far away. And if you wait too long, you won't have enough fuel to actually change the trajectory. So they sent many of us to places like South Africa, Argentina, Colombia, trying to intercept the shadow of a Kuiper Belt object, which eventually we succeeded in doing. It's called Arrokoth. Its original term was MU69. And Arrokoth is the most distant object ever photographed successfully by mankind. And it's a binary asteroid. And some of this equipment that you see in the boxes on the walls is the old equipment that was being used for those missions. This is Lucy Occultation Headquarters in Longmont, Colorado. And you can see the walls are just lined with all kinds of equipment. I'll ask my wife to note that our garage doesn't actually look like this yet. So it's not as bad as you think, honey. But this stuff has been shipped all over the world and then successfully shipped back and reused over and over again. I've been on some of these events. The Dunhams have been there. Wayne Thomas has been in some of them as well. So we loaded up our car with our set of equipment, which was Telescope 56, and we headed out to the area south of us. This is an animation of what we expected to happen on the night of August 11th. The shadows of these binary asteroid components are drifting across the planet Earth, and our job was to be in the right place at the right time, in a place where it wasn't cloudy, to observe a star disappearing behind those asteroids. And each one of those little lines, the purple ones for Patroclus, which was the team I was on, and the yellow lines for Menoetius, its binary partner, each of those lines represents one team. And our job was to be somewhere along that line observing the star. That means that we would get multiple cross sections of the asteroid as it drifted in front of the star. Why so much driving? Oh, the weather report. On the right, you see the Canadian forecast for our area. The red outline is New Mexico. And we were at that red dot up there in Longmont, Colorado when we picked up our equipment. It was obvious that we really had to go somewhere. And we had to go somewhere that included intersecting those two long green lines, those shadow paths. So we had to drive south. And you can see when we, on the first day, we drove for about 6 hours. And about 3 hours into our drive, you can see we noticed the blue sky out ahead of us. And that's what we were heading for, trying to stay in that blue sky for the whole time. We did go through Roswell, New Mexico. I encountered these friendly creatures. The probing wasn't as painful as I thought it would be. We did stop at the International UFO Museum and Research Facility. If you ever go there, you'll be a great laugh. It's only $5 to get in. I thought it was worth it, and we had a lot of fun in there. Excuse me, checking out the arrivals. Here's the equipment we used. These are Celestron CPC 11 scopes right off the shelf. The laptop that you see on the left runs SharpCap and ASCOM to talk to the hardware. And on the right, you see we've got the secondary mirror removed, a Hyperstar from a Starzona attached to the front, and a QHY 174 camera that has a built-in GPS antenna. So each digital image that's taken is timestamped with the millisecond accuracy of GPS timestamps that's obtained from GPS satellites. So we know if we do get an occultation, we know exactly when it disappears and when the star reappears as well. So the result of those combination of optical training is an f2 11-inch aperture telescope. So very fast, lots of light gathering ability, tight, fine stars, and a wide field of view. Just what we need when we're trying to find these faint stars. And here's a picture of it from the front. Lots of wires. Figured out what went where after the first night of practice. Set up, and we were set up about an hour early. So here's our assignment. It's a 5-part assignment. All right, we have to record for 6 minutes of data at 200 milliseconds exposure. So that's a cadence of about 5 frames a second. Because any shorter than that, we wouldn't be able to see the star. Any longer than that, we'd give up some time resolution. So we had this trade-off, and Mark Bowie, the scientist in charge of this whole project, eventually settled in on 200 milliseconds after our first few nights of practice. So 5 hyperseconds, starting at 10:30, 3:30 universal time. That's about 3 minutes before the predicted time of the shadow passing over you. While you track the star, of course, you want the star to be on the screen when the event happens. And you have to be somewhere along your chord, plus or minus about 400 meters left or right from the chord to get even spacing of the occultations. This is our first practice night on day 1 or night 1 at 3 o'clock in the morning. So we drove 6 hours, got a couple of hours of sleep, and then headed right out to the field. On this particular first night, all of the people with their telescopes went to the same place to practice together because some of us had more experience than others. So we could help the beginners kind of figure out where the wires went and how to use SharpCap. It was really nice because they had programmed the RA and deck of the star into SharpCap. So we let SharpCap do a plate solution and drive the scope directly to the star. We didn't have to star hop. We didn't have to do an alignment. Everything worked perfectly, and we did well.
Have a menu thing.
Oh, thanks. Great. That was night 1. By the time we got to day 3, we were all very experienced and very tired. We did have one all-hands meeting at New Mexico State University in a classroom where Brian Keeney, who's the scientist in charge of our team, was giving us a little weather briefing and talking about our plans. So this was our last practice night before the event. And so this was dress rehearsal. Go out at the time the event was supposed to happen tomorrow night, pretend it's event night and make sure everything goes well. And turn your data in so they can double check it. We had a couple of extra meetings as well. There's really good Mexican food in New Mexico. So we had some light, everybody's got to eat. So we all tried to get to the same restaurant now and then. Here was our chord. It was chord number 14 out near the northwestern edge of this shadow path. Each one of those lines represents another team that was out in their Chevy Suburban or whatever car they got rented from Avis with equipment in it. Everyone's scouting different places. We scouted 3 places to cross our path. The little black circles, we decided to use the one farthest south, right off of I-10. Because we thought the farther south we go, the less chance there will be a cloud at just the wrong possible time, the worst possible time. Here's a view of our site. We set up our scope on that X. Luckily, there was that nice purple line painted right on the road when we got there. Yeah, it was very, very nice of the team to do that for us. We had perfect skies, the nights of practice and the night of the event as well. On event night, we set up our equipment. I was lucky to have two University of Virginia students with me, both astrophysics majors, and they were happy to lug all this heavy equipment around and set it up. I was the brains of the outfit. They were the brawn. But they actually knew everything. I just watched them. They set everything up. They knew how to operate the software. They'd done this several times before. Because there's a team at the University of Virginia that does occultations as well, supporting Southwest Research Institute. We were set up an hour in advance, and we just waited. Here's what our screen looked like on SharpCat. While we waited, we were tracking this field of stars, and the target star that you can see right there on the two red lines, that little dot represents three sources of light. There's starlight from the star behind the asteroid, which hasn't quite gotten there yet. But at this point, the two have merged close enough that they just look like a single object. And added to that is the reflected light from the two binary asteroid components. So those, when they add together and they get close enough, it just looks like a brighter star than it would be if the asteroid was somewhere else. The star itself was magnitude 12.8. So it's pretty faint. So that's why we needed an 11-inch telescope to just see it at 200 milliseconds of operation. And here is the actual data that we saw. Keep an eye on that by the two red lines. So now it faded out, but there's a faint image there. That's the reflected light just from the asteroid, because the star is now behind the asteroid. And 10 seconds later, the asteroid moves off the star and it reappears. So let it play one more time for you. The asteroid is like magnitude 16 or 17, so it's out there. So when you analyze data like that, you get something called a light curve. And I just grabbed 5 light curves from 5 of the different teams all around these various chords. You can see in each of these red circles is the drop in intensity of the light. Most of the light here was obviously coming from the star, because what you see in the lower part of each of these graphs is the light reflected from the asteroid. And then when the star reappears, you get the combined light again. Now, a day later, the two of them will actually be separated in space, and you'd be able to see them side by side as the asteroid continued to move off. But during this entire effort, the two of them were completely merged into a single object. They were just too close to resolve totally. Here was the happy team. This is P14. Adam Schrader and Nick Velasquez were my two compatriots. We were very happy that we got data. We actually saw the disappearance on the screen. We watched it live, turned in our data, and got and headed out for home. That was our chord there on P14. So we were up near the northwest edge of the asteroid. We saw that. That was our measurement. The team at chord 15 also got a positive recording. So they were closer to the edge, and it turned out that the team at chord 16 saw a miss. So they never saw the star disappear at all. So their miss is the most important negative observation of the entire occultation campaign, because now we know that the edge of the asteroid, it has to be somewhere between line 15 and line 16, because line 16 was not occulted by the asteroid. So that's important. There were 11 positives on Patroclus and 13 positives on Menoetius. I've been asked not to show the actual data because it's still embargoed and it's still being analyzed, and it'll be published in October at a conference. And once October comes along, I'll send out a note to the club and say, here's what the actual shape of the asteroids look like. But they were very happy with this result. And this is what the odometer on the car said when we turned the car into Avis 4 days later, 2,024 miles, dodging clouds and so on. Back in 2015, when we didn't know the location of this object as well as we do now, they sent out another set of about 30 telescopes, but we had to have a much wider spacing to be sure we could catch the actual occultation. So you can see how far apart these chords are. and only 4 or 5 positive chords on each object. But this was enough to improve the orbit enough that we knew exactly where these shadows were going to be in 2024. So we were able to put all 15 of our telescopes in a place where 11 or 12 or 13 of them were going to get positives. And we got a really good set of chords across the asteroid. So that was back in 2015. So this is the list of authors on that paper. And you can see there are 7 authors from SWIRI and Southwest Research Institute and other institutions, but every field observer becomes a co-author if you choose to be. So our names are on certain of these publications in things like the JOA and so on. So it's exciting to do that. Back in 2011, I'll just point out that there was another binary asteroid that IOTA, the group that I work with, International Occultation Timing Association, went out for an occultation of a very bright star, 7.6 magnitude, by a double asteroid that crossed the state of California. And you can see how many positives they got on this particular event. In fact, you can see that the southern half of Antiope here has a huge crater on it. There would be no way you could determine that existed using optical or radar kinds of reflections, but occultations give you very accurate measurements. Something like plus or minus 1 kilometer at a distance of 400 million kilometers. Amazingly accurate. So this is the IOTA web page. I know David has given talks here in the past on occultations. I'll just reiterate that new observers are always welcome. The more, the better. This is a way to do some real science with equipment you already own. And we can help you with the camera part and the timing part and all that. But if you've got a big telescope or even a small one, for occultations of bright stars, 80 millimeter scopes are fine, or 120 millimeter, 3-inch, 5-inch, that kind of stuff. Stick a camera on the back, point it at the right place, and you can participate in this kind of work. We'd love to have you. You can follow the Lucy Adventure on their websites, on Facebook, Twitter, Instagram. Hal Levison, who provided these beautiful fancy slides, is the principal investigator for the Lucy mission. And he's the one greatly anticipating arrival at the Trojan swarms in about 3 years from now. So thank you. Appreciate you taking the time with us. We have time for a few questions if anybody has a question. Yes, sir. Yes, the light curves were recorded by SharpCap. Each point on the light curve is a FITS image, a FITS file representing the star field for 200 milliseconds. So as the software that reads that is called PyMovie, and you can set an aperture over the star and it measures the light in that aperture for each image and creates that blue graph. The star disappears, the graph goes down, and goes back up, and we know the exact times. So that
show something, I don't know, having position. Well, like a something, I don't know, they use it for.
well,
Ted, could you summarize the comment?
oh, sorry. Yeah. The question, sorry, yeah, for our folks out there, the question is there was some kind of an extra object on the C11. Well, I'm trying to remember. All we had on the front of the C11 after carefully taking off the secondary mirror and putting it in a box was screwing the hyperstar onto the threads and then screwing the camera onto that. There wasn't anything else that I remember setting it. Well, there might have been, there was a metal weight that was placed on the back of the telescope to balance it, because the telescope would be very front heavy with all that equipment on it. And so there's actually about a 5-pound metal shaft that you screw onto the visual back on the back of the telescope that just clears the scope when it goes vertical. but that provides enough counterbalance that the gears don't have to work so hard, the motors don't have to work so hard to move the telescope. Otherwise, it would really be front heavy. There's about, I'd say the Hyperstar and the camera together weigh about 7 or 8 pounds, and that's a lot of offset weight. Yes, sir.
Does that actually distance between them?
So the question is, does the actual ground track indicate the actual distance between them? And yes, it does. They were that far apart. They're about 1 diameter apart at this point in their orbit. If the occultation had occurred at another time, they could have been following each other along the same path. They could have been one in front of the other, or partially overlapped, and we would have to be stuck with whatever position they were in. But luckily, they were separated. Even the tiniest separation would have been enough, but we had a nice wide separation. Half the team had to go to Texas to be able to be in the path of the Menoetius component to get clear weather. We were in Las Cruces, New Mexico, and at the end of that event, everybody had about a 10.5-hour drive to get back to Colorado to turn in the equipment on the same day. So thanks.
Okay. I study exploration systems design or instrumentation, which is a fancy way of saying that I build like telescopes and cameras for astronomy and for astrophysical observations. Like another way of saying it is like instrumentation or astronomical instrumentation spans a very wide range of wavelengths. And so I'll talk today about 2 different projects and two different instruments that study at 2 different wavelengths and have 2 different science objectives. So first I'll talk about the Lucy mission, which Ted has already talked about a little bit today. I'll talk specifically about how Lucy observes our solar system and the asteroids in our solar system using optical instruments such as cameras. And then I'll talk about Dora, which is a student-run CubeSat mission, which aims to observe the creation of the first stars in the universe with a radio telescope. All right, so first I'll talk about Lucy. Ed already gave a really good overview about the Lucy mission, but I'll give a background maybe more focused on the instruments that are on Lucy. So it launched back in October 2021, and it contains 3 scientific instruments and 2 additional engineering instruments that we can also use for scientific purposes. The first one is LaRalph, which is a color visible imager and an infrared spectrometer. And then we have Lori, which is a high resolution spatial imager, or like a high resolution camera, basically. We have Latesse, which is an infrared spectrometer. And so in addition to those 3 scientific instruments, we also have a high gain antenna used for communications, but we also can use it to determine masses of the asteroids using like a Doppler shift. And finally, we have the terminal tracking camera, which is used primarily for target acquisition and navigation, but we also use it as a camera for scientific observations. So Lucy is planning on flying by 8 asteroids total, plus some satellite asteroids, so 8 to 10. 6 of them Trojans, and the first 2, Dinkinesh and Donald Johansen, are Mainville asteroids, and I will talk a little bit about Dinkinesh at the end of this presentation. So I'll give a very brief overview about what the Trojan asteroids are. Again, Ted gave a very good overview of this, but essentially, because the Trojan asteroids are at Jupiter's Lagrange points, they're in very stable orbits in around the sun and in the solar system. So they're regarded as a really good opportunity to learn more about the history and the formation of our solar system, and even possibly about the origins of organic material on Earth. Together, these slides, I found this really good graphic online of the Lucy mission. This is actually a little bit out of date. It says the first asteroid encounter is in 2025, but actually we already had one in 2023. But I think this is when the Lucy mission was first proposed or first starting, but it shows like it gives you like a good picture of what the satellite looks like. It's almost 16 meters wide with both solar panels completely deployed. And you can see the path that Lucy is supposed to go on, where it kind of winds around Earth 2 times for like an Earth gravity assist before going out to the Trojan asteroids in Jupiter's orbit. So the terminal tracking cameras, which I mentioned before, are what I'm going to focus on today because that's what I worked on. They're primarily used for flight engineering, they're used for navigation, but because they're wide angle cameras, they are super useful for scientific objectives as well. When we use them at close approach to the asteroids, we can learn about like the shape modeling and the target's geology of each asteroid. So before I get into like the data that we're getting from the terminal tracking cameras in flight, I'm going to talk a little bit about what we did pre-flight to calibrate these cameras and get them ready for scientific analysis. So most cameras, when you take a picture, you get a pixel array. You get an array of numbers, and these numbers don't mean anything intrinsically. And so our job as instrumentalists, our job before we put the camera into flight was to make sure that we understood the camera's response enough that we could convert that digital number given to us by the camera into a physical like intensity number or radiance number. So for when we take pictures of our asteroid, we can look at what that intensity is of the asteroid and like know physically what intensity it is. This is a very kind of complicated equation, but really all it's telling us is dn is what the number we'll get from the camera, and that number comes from a bunch of different properties intrinsic to the camera, such as like how big the lens are, how far apart they are, and also things that are intrinsic to the electronics of the camera itself. So another way of looking at this equation is that if we know what the digital number is, if we have a picture of an asteroid in front of us, we want to get that number and convert it to a physical number of radiance or intensity, which is that L on the left side of that equation here. And so this equation on the bottom forms the basis of what we call the calibration pipeline for the T2 cams. This is another way of looking at the calibration pipeline using blocks instead of an equation. I'm not going to go into detail about this too much, but basically what I have this here to show is that we get directly from the T2 cameras an uncalibrated data product of just digital numbers. We go through a process of correcting it for like noise or for any like irregularities in the optical chain, and we do some conversions to convert that digital number into physical radiance, and then we get our calibrated data products. And this is applied to every image that we get that we want to do scientific analyses on. So any navigation or target acquisition system won't really care about this process, but the scientists who are studying these asteroids do care about this.
The question of what does DN stand for?
Okay, DN stands for digital number. So it's just the number the camera gives. The camera will assign a number based on intensity to every pixel on an image, and so that's the DN that the camera gives that we're trying to calibrate to a physical radiance unit. I have some plots here showing the types of pre-flight calibration data that we collected. I won't go too much into it, but I'm sure some of you astronomers in the audience will recognize that I'm showing flat fields and I'm showing dark frames, for example. So flat fields would show any irregularities in the optical chain that we can then calibrate or divide out in our final product. And these plots down on the bottom right shows the noise that's inherent in the camera electronics. And then the plots to the left show kind of the conversion between like digital numbers from the camera and electrons and photons. And this final step in our pre-calibration, or sorry, in our pre-flight calibration routine is to make sure that we can then convert our units of radiance into I over F. And all I over F is a measure of reflectance with where like L is our measured radiance, and we're basically comparing that to the intensity or the irradiance of the sun. So it's just an easier way, it's an easier way and a more it's an easier way of looking at a figure and getting these I over F values, where you can say, oh, this is how the intensity of this compares to the sun, instead of just having a number that is the physical radiance of the object. So that's the in-flight, that's the pre-flight calibration that we've done with T2 cams. Lucy launched in October 2021, and since then we've had a long period of cruise where we haven't seen any asteroids, and we use that to refine our calibration and to validate that what we did pre-flight did work, and that we were getting numbers from our calibration pipeline that made sense. So first, just 20 days after launch, we got our first images. This is just of the star field. I don't know if I mentioned this, we actually have two T2 cams on board. One of them is a primary flight. Am I like, sorry. One of them is a primary flight camera. And then we have a secondary camera, TT Cam 2, that's meant as a backup if the primary camera ever fails. 120 days after launch, we got some more images. This is one of my favorites. It shows the Rosette Nebula. And finally, a year or so after launch, we had our first Earth gravity assist, which is when the spacecraft comes back to Earth and uses the gravity of the Earth as like a slingshot to bring it out further into the solar system. This is the first of two, I believe. These are some of my favorite images from the Earth gravity assist. There's in the center, there's the Earth. To the right, there's a moon. And to the left, the Earth and the moon are actually in the same frame. I have a more zoomed up picture here, which I love this picture because you can see kind of the difference between the sizes and most importantly, the intensity between the Earth and the moon. So this is my favorite picture from Earth gravity assist, but the most important picture to the scientists in terms of validating how our cameras worked and how our calibration pipeline worked was the picture of the moon, actually. The moon is a very well understood rock, essentially. We know exactly what we expect to see from the moon. We know exactly what the radiance of the moon is and what the reflectance of the moon is. And so we were able to, since we knew we knew at what angle and at what time we were approaching the moon, one of our team members was able to make a modeled what TT Cam should see of the moon. And that's to the left here. And then in the middle, the center image there is the actual image that the TT Cam took. I cropped and rotated these so they're like exactly aligned with each other. You can see they're very, very close. There's maybe a little bit of shadows that are a little bit off, but you can't get the model to be perfect, as always. And finally, we looked at the correlation between these two images and proved that there's a very high correlation, which essentially proves that the T2 cams are working as expected. And also, not only that, our calibration pipeline is working as expected. Okay, and then finally, I talked a lot about T2 cam and about validating T2 cam and making sure it was ready for science. Last year, we finally got some of our first science data. Dinkinesh was a small main belt asteroid. We actually weren't planning on flying by this asteroid when the mission was first conceived of, but it happened to be in our path. And the main purpose of flying by Dinkinesh was actually to test our target acquisition or navigation system. So it wasn't really for science. The good thing is the target acquisition and navigation systems works. And we also got some really cool science out of it. So it was revealed to be very unexpectedly complex. We thought we were going to fly by like a kind of a simple, small main belt asteroid to test our target acquisition and nav systems. We ended up finding like not only some really weird like troughs and ridges on the asteroid of Dinkinesh itself, we also found that there was a satellite called Salem or Salam. I'm not sure how to pronounce that. And it was not just a regular satellite, it was a contact binary satellite, which we haven't really seen before. What I mean by contact binary satellite is that, as you can see, so these pictures, where's my laser? As you can see here, these are pictures of Salem. It looks like there's like two satellites or two asteroids kind of stuck together. They almost look like two separate asteroids, but they're not. They're actually in contact. They're one asteroid. And there's like many, so there's a few different ways something like this could form. It could be that two separate, from Dinkinesh, like some type of secretion from Dinkinesh, like ended up with two separate satellites that eventually like crushed together. Or it could be that Salem was actually just one, ended up just what started out to being just one secretion from Dinkinesh that ended up kind of through like some other forces, through like centripetal force or whatever, kind of elongated out into two separate lobes. So it's not super clear what happened, but it is super interesting. It shows that there's a lot more like secretion and accretion going on in small main belt asteroids than we previously thought. I'll also point out here, these are pictures of Dinkinesh. They were taken by LORRI, not by T2 Cam, because LORRI is the more high resolution imager of the two. And you can see the purple dots here are where there's kind of like a ridge, and then the yellow dots there kind of show like a trough where perhaps parts of Salem were started off at, and then were then secreted from. Okay. So what's next for Lucy? I mentioned that we had one EGA, one Earth gravity assist out of two. The next one is coming up later this year. So I'm excited for more pretty pictures from that, and also more opportunities to refine and to validate our calibration. Next year, we're gonna fly by another main belt asteroid called Donald Johanson, which was planned since the beginning of the mission, kind of to do what we did with Dinkinesh. It will be a second test of our target acquisition or nav systems, just to make sure that all of our instruments are working as expected. And finally, in 2027, we're going to finally fly by the first Trojan asteroids, hopefully long after I've graduated. But okay, so that was Lucy, and that was the first instrument, which was a camera and an optical instrument. Next, I'm going to talk about cosmology, specifically 21 centimeter cosmology, and doing that from space. So before I get into the nitty-gritty of this, I'll say first that what I just presented on, Lucy and T2 Cam, is a huge NASA mission with a lot of funding. T2 Cam was already built when I came onto the project, and what my job was mostly to validate that it was working and to calibrate it and to make sure that it was usable for science. 21 centimeter cosmology is a much smaller field than planetary astronomy is, and we don't have the same type of funding that Lucy did, for example. So a lot of the research going on in 21 centimeter cosmology, especially the research going on in building instruments for this field to go to space, is a lot of prototyping and a lot of pathfinding. So a lot of the instruments that we're building in this field, while we might not be able to find or to observe the signal that we want to observe, will help us develop the technology to get there eventually. It's a much smaller field. And so with that in mind, I'm first going to introduce the field to you. To do that, I'm going to start out with the cosmological timeline. Everyone knows the universe starts with a Big Bang. After the Big Bang, there's a period of hot soup, as I like to call it, where the universe is expanding rapidly and also heating up rapidly until it comes to a point where the universe starts to slow down in expansion and starts to cool down significantly. And we enter a period of time called the Dark Ages. So sometime after that, the first astronomical objects and the first stars start to form. And those first stars start to reionize the hydrogen in the universe during a period of time we call the epoch of reionization. So as the universe reionizes, more and more astronomical objects form and galaxies start to form, and then we finally get to the universe as we see it today. But what I'm super interested in is this period of time when the first stars started to form, called cosmic dawn, and the period of time following that, where the first stars then start to reionize the hydrogen around it, which we call the epoch of reionization. So why do we call it 21 centimeter astronomy if we're looking at cosmic dawn and the epoch of reionization? Well, that's mostly because the most common element during that period of time is hydrogen, and so we want to observe hydrogen. And it turns out that neutral hydrogen emits this radiation at 21 centimeters when its single electron, basically the hydrogen atom has a single electron and it has a neutral state and kind of a spin flip where the spin flip of that electron flips a little bit, and that flip emits radiation at a wavelength of 21 centimeters or a frequency of 1420 megahertz. And that just so happens redshifted down to where we are now. That just so happens to fall in the radio spectrum. And so astronomers who are looking at hydrogen during this period of time are radio astronomers, and we study a pretty large range of wavelengths from 0 to 200 megahertz. So I'm going to go back here really quick. So there's this cosmological timeline. We're going to see hydrogen throughout this timeline, but we're going to focus on this like period of time right here. And so if we look at hydrogen throughout the entire timeline, we're going to see something like this that I have up here. We can look at it in two different ways. We can look at the spatial fluctuations in hydrogen throughout time, or we can look at the total average power of hydrogen like over the entire sky versus time. So if we want to look at spatial fluctuations, which I have on top here, we would need an interferometer to look at the spacings between like different intensities of hydrogen, and in addition to like a time dependence. Or what I'm focusing on is looking at a total global power measurement of the 21 centimeter signal. So you would just need a single antenna that averages what it sees over the entire sky, and then plot that versus time or redshift or whatever. And it's theorized that you would see something like this, where this kind of right here kind of corresponds to when the first galaxies formed, the first stars formed, and then this over here corresponds to epoch of reionization right here, and then here would be modern day universe. So there are a few current experiments that are trying to detect this global signal right here. ASU is working on one called EDGES, the experiment to detect the global epoch of reionization signature. This is a terrestrial instrument, it's a terrestrial radio antenna, radio telescope in Western Australia, kind of in the middle of nowhere. This is what it looks like. I don't have a size scale here, but this is about, oh no, I do. It's just really small. This is about 1 meter by 2 meters. And then this box right here holds all of the front end electronics for this telescope. So I mentioned before that I want to do 21 centimeter experiments in space. Why do I want to go to space? Well, looking at these pictures of EDGES, you can see that it's not completely uniform The telescope itself, we try to build as uniform as we can. We try to have a ground plane here made of mesh, but things such as the shape of the horizon, the fact that the ground plane isn't infinite, the soil, like even like wetness in the soil, whether or not it's rained, vegetation on the horizon, all of that leads to really difficult to model inconsistencies in our data. It's since the 21 centimeter signal is from so far away, like it's from a long time away, it's such a faint signal that even small inconsistencies such as all of this will make a huge difference in our final measurements. So EDGES has arguably made a measurement of the 21 centimeter signal, but no other 21 centimeter experiment has been able to confirm that measurement, possibly because no other experiment has been able to reach that that level of like detailed analysis and detailed modeling of their instrument. Even with EDGES, it's very, very difficult to get there. So there's all of this like inherent in building the instrument itself. It's a huge task to try to get that detailed and that specific. But in addition to all of this, we're radio astronomers, so we are dealing with a lot of human-made interference as well, specifically like from FM radio, from TV stations, from all of that. And it's very hard. That's why we're in Western Australia. It's as far away as civilization as we can get. But even then, it's very hard to get rid of like all the RFI, all the radio frequency interference, all the FM radio, and all the TV stations. Like even if like to the horizon you can't see anyone, there's things such as like interference from like possibly just over the horizon, being reflected off of planes or being reflected off of towers. So human interference is really hard to get away from. Some other 21 centimeter experiments have also tried going to the Arctic. That's worked better than Australia, but the idea is we could do even better by going into space to get away from human interference. Here I have kind of a roadmap for what going into space would entail. You would think we would start out with balloon testing or like balloon experiments, where we would get as near space as possible, mostly for technology development and for testing. From there, we could get into a low Earth orbit, possibly on a CubeSat. And there's even been some proposals for a 21 centimeter experiment on the far side of the moon, where the moon would kind of act as a barrier for RFI. So there's a lot of pros and cons to going into space. I'm focusing mostly on the pros because I think it's a good idea, but going to space does mean that we have to miniaturize our experiment drastically. So the EDGES, which I showed before, I said was like 2 by 1. The antenna was like 2 meters by 1 meter, and the electronics box is on the order of like 5 pounds or something. It's very heavy. If we want to go into space, we need to miniaturize that significantly. So we started to do that first by miniaturizing EDGES as much as we could and putting it on a balloon to test if our miniaturized instrument would work in like a space-like environment. So short-term goals of putting it on the balloon, I kind of went through this, but we wanted to miniaturize it. So not only reducing the size of it, but also the weight and also the power that it needs to operate. So one of the biggest constraints we had on the balloon was how much power we could use, and also how heavy our payload could be. This is a first iteration of a miniaturized EDGES instrument. I won't get too into the details of this, but basically here is a block diagram of the EDGES instrument, which was like the big instrument in Australia with the like 2 meter antenna here and this like 5 pound box here. We miniaturized it to an antenna that was only about 5 inches by 3 inches in size. We took that giant box full of electronics and miniaturized it to a single board And for all of the, and for the rest of it, we miniaturized into, instead of using a spectrometer, like a custom built spectrometer and a PC, we took an off-the-shelf software-defined radio dongle, which is this thing here, and an off-the-shelf Raspberry Pi. And this is like our first iteration at a really small, really cheap 29 centimeter radio telescope. This is a block diagram of our new system. I won't go through that too much. But okay, so in October of 2022, we were able to do a first balloon test flight. We did this with as part of the local ham radio festival in Maricopa, where they have a group of like ham radio enthusiasts who like to I don't know, like have these weather balloons, and they're really good at chasing these down actually. So one of the hardest things we wanted to like fly our own balloon, but we couldn't figure out how to make sure we were accurately tracking that balloon and accurately determining like based on weather where the balloon would go, and also figuring out like how to retrieve that balloon after it fell. So the Ham Radio Fest organizers figured all of that out for us, and we kind of piggybacked off their balloon flight. And it launched in Maricopa, and we retrieved it like way out here past Florence. Landed in a bunch of cactuses. You can see it got like pretty high. It got up to like 100,000 feet in altitude. And then we did a second balloon test flight after that in January of 2023. We launched out of Quartzsite this time, but also with a local Hamfest who did like a very similar thing. We made some like minor adjustments to our first iteration, which is that we added some more opportunities for like telemetry observations and telemetry data. And we replaced our off-the-shelf Raspberry Pi 3B Plus with another off-the-shelf Raspberry Pi, but one that allowed us to make some adjustments to like the inputs and outputs. So lessons learned from balloon flights. As I mentioned before, the balloon flights were more meant for technology development than for like finding any exciting science. But from technology development, we could learn where we were lacking in making a miniaturized instrument. One of the biggest things was power. We needed like a better way of turning power on and off, and of conserving power, because we're using up a lot of power even in just one flight. Secondly, from the second flight, we fixed some of our power issues, but we found out that we were using like cheap, like off-the-shelf electronics that had a lot of noise inherent in the system. So obviously that's a big issue. That's the first thing I mentioned, that like we need to know our instrument super, super well in order to do any type of 20 centimeter cosmology. So in terms of technology development there, the next step would definitely be to develop more on the radio, the software-defined radio side, to make sure that we understand our instrument. If not develop our own, at least to understand it fully. So I talked about the balloon testing part of it. Now I'll talk about putting our experiment on a CubeSat. So I'm gonna step back a little bit. Going from a balloon to a CubeSat is kind of a huge jump. It was not a jump that we were really expecting to do, but since we got this opportunity to do it, we realized we had the opportunity to not only just develop the technology of our miniaturized instrument, but also to do some science that would help in like a future 21 centimeter a future bigger 21 centimeter project. So I've talked a little bit about like RFI interference, or radio frequency interference, and how much that messes with our data. This is like some proof of it. This is edges in Australia, and these graphs here are like a percentage of the data that we retrieve. So data that was not messed up by interference, human-made interference. So like at lower frequencies, we get 100% of the data. It's fine. Once we hit like the FM band, it goes all the way down even to like 0% at some points. And then up here is possibly TV or ORCOM or like satellite communications that are also interfering with our data. So this is in Western Australia. This is like kind of in the middle of nowhere. Even in the middle of nowhere, we don't get a huge, like great data retention at FM band or some of these bands here. So like one thing we thought about was putting it on a balloon, not like the weather balloons that we were testing on, but like a super high pressure balloon, such as Superbit, which is a NASA, like I think it's another cosmology experiment that NASA possibly did, but it launched a couple of years ago, and a couple of years ago, and it followed like this rough orbit over here, where the blue circles kind of represent the field of view it had of the Earth. So you can see there was a lot of times where it was just kind of over the ocean, the Pacific or the Atlantic, where you couldn't see land at all, and it couldn't see any people or any civilization at all. So if we were able to get on a balloon like that, we did some like quick simulations of like how much civilization and how much FM radio we would be able to see over like the same amount of time. Like let's say like this is over like 1 day, like if this was also over 1 day, then what percentage of our data would have to be thrown out because of FM? Because a balloon would be like moving over the ocean or places of where you can't really see people for so long, the percentage of data that we would not be able to use is much, much lower than if we were to stay still at one spot in Australia. So that's if we used a balloon. We also thought about, okay, well, what if we use like a satellite in low Earth orbit, such as one like following an orbit very similar to one of the ISS. So this is a simulation that one of our undergraduate students did. He took the orbit of the ISS and simulated what types of RFI the ISS might see over like a period of a couple of days. And so this is a different type of graph than what I showed before, but it shows basically the same thing, where this you can think of as a time axis, and this is frequency. And this is kind of a little bit different from the past graph, but like this shows like the brighter it is, the more RFI you have, essentially. But there are still some parts, like there are still some times like up here and here where you don't see RFI at all. So it would still be it'd still be something that we can look into as a method of getting somewhere with less RFI. So given all of that, we were given the opportunity to launch our payload on a CubeSat, kind of out of nowhere. So Dora, the primary mission of Dora was actually to test and to develop technology of an optical laser receiver for inter-spacecraft communication. This was a collaboration between JPL and ASU. The interplanetary lab at ASU was like heading this collaboration. But COVID happened, and JPL couldn't get their stuff done, and funding ran out, et cetera. And so they had like a bunch of extra room on this spacecraft that we were then able to put our payload into. So that's kind of the story of Dora. That's how we got space on Dora to put our miniaturized radio telescope onto. This is Dora in the lab. It's small. I should have put a size scale on here, but it's like the size of like a large water bottle, like maybe like a larger Stanley water bottle or something. It's I would want to say 3 inches by 3 inches or 4 inches by 4 inches the sides. This is that same block diagram of edges, which I showed before, except this is a new iteration where we took some of the same things that we did with the balloon payload. So we kept our Raspberry Pi and we kept our off-the-shelf SCR dongle right here. But we made some differences. We made some changes to our single board, like filter bank and like electronics here, and we changed our antenna from like a simple patch antenna that was just like a copper board that you saw before to a this is a tape measure antenna actually, and so it'll open at some point when we decide we want it to open, and then a tape measure kind of will spring out, and it'll just act as a dipole for our payload. This is a block diagram, which I won't go too much into, but what I really want to show is that this is an entire spacecraft, and our payload is actually just this top, like 5 or 4 boards up here. So it is miniaturized. It is much, much smaller than what we flew on the balloon. And I think it performs better. One thing I did mention with the balloon spacecraft was that we were having a lot of power issues on a CubeSat. Our power issues were amplified. We had much less power than we did on the balloon. So we had, like I said, an off-the-shelf radio, software-defined radio, that we were taking data with. It would give data such as this. So you can see it's pretty high resolution, going all the way from 0 to 200 megahertz. But we can't run that all the time due to power constraints. So in addition to a software-defined radio, we also have a very low resolution filter bank. These two actually span the same frequency, but there's a lot less data points on this one than there is on this one, which will allow us to constantly monitor the frequency, constantly monitor the power in our frequency channels, even when we don't have that much power. So I show these are data that I've taken with our payload and with Dora in the lab. I show these to show, like, you can see there's like FM right here and FM like right here. Channel 3 kind of corresponds to like right here in terms of frequency. So you can see, like, in the lab that there's obviously FM. What I'm hoping is that Dora will see in orbit almost a perfectly flat spectra, both here and also here, which will prove that there are some spots of orbit, hopefully like above the Atlantic Ocean or Pacific Ocean, where human interference isn't a problem. You can't see any type of human-made RFI. This is a quick slide on the system performance of Dora. We finished up thermal vacuum testing and testing the power and the data budgets back in April. Everything was working as expected. And we actually delivered to NASA back in May. It went through some vibrational testing up here where they strapped the entire spacecraft onto a table and shook it a lot and made sure nothing fell off. Something did fall off, but it wasn't important, so it passed. It launched just a week and a half ago on August 4th on one of the resupply missions to the ISS. NASA runs this program for student CubeSats where we can kind of piggyback off of an existing launch to the ISS. So we piggybacked off an existing launch to the ISS, and currently it is sitting on the ISS right now, waiting on some last minute paperwork to get done, and hopefully it'll get deployed sometime in mid-September, but it may get pushed back to November. So that's it for Dora, and I'll open the floor to any questions.
Question.
Okay, sure. Yeah.
Will the actual launch from the ISS be accomplished?
So the question is, how will the actual launch from the ISS be accomplished? I'm not 100% sure, but we loaded up when we brought Dora to NASA. We loaded Dora up. You saw it's kind of like a rectangular shape. We loaded it up in like this even bigger rectangular hollow tube thing. And I think they literally shoot Dora out of the tube. That's all I know about it. Dora has its own like attitude control system. So ideally, once it's shot out, we can like kind of orient ourselves so that our solar panels are facing the sun and start getting power and start operating. Yes.
What about experience from?
That's a good question. The question was, do we have to worry about interference from the ISS itself? Is Dora going to be far from the ISS? And yeah, Dora is going to be far from the ISS. It'll be launched from the ISS, but our orbital path will differ a lot from the ISS. And in that case, like, we're not only worried about the ISS. There are so many satellites up there right now. There's like, all of Starlink is up there. So Yeah, but that's a good question. I don't know how much those satellites will interfere with us. And so that's something else that hopefully we'll find out with our data.
Data.
Yes. Yeah, so the question is, are we getting real-time data acquisition? Is there like a monitor at ASU? We do have a ground station at ASU. It's we are very limited, so our data budget is very limited because we're only able to downlink our data when we can see Dora directly, like in the sky above us. There's the CubeSat, like the student CubeSat community is kind of cool. There are like a bunch of ground stations all over the world that are automated to like downlink data packets every time they see a satellite or a CubeSat that's on their list essentially. So in addition to our own ground station, we're hoping that other ground stations around the world will be able to download some of the data for us. The question was, what's the life expectancy of Dora? The answer is, I don't know. But when we told NASA that, they didn't like that answer. So I think the nominal life expectancy is like on the order of months. They aren't expected to last very. Yeah.
So which of these two is your actual?
The question is, which of these two are actually going to be in my dissertation? Both. Yeah, but I am focusing. I started out my grad school career with Lucy, and I started focusing more on radio astronomy, like in my second or third year. So the majority of my dissertation will be on 21 centimeter astronomy. Yes.
I think I.
Yes. To the various, okay, so the question was 15 watts was our power allocation. How will that be distributed among the various like systems of Dora? I'm not super sure. I know that our system specifically gets about 4 or 5 watts. So obviously like attitude control, everything else, like the flight engineering aspects of Dora need power, but there's about like 4 or 5 watts left over for our payload.
.21 centimeter detection, is that the morphology of that particular region of university of that layer?
Yeah, that's a good question. The question was like, what's the goal of detecting a 21 centimeter signal? I mean, really the goal in general with science in general is that we have this theory. We think that that's what, maybe I can go back really quick. We think that we know what the 21 centimeter signal is going to look like, but we don't actually know for certain. And there's no proof right here. There's no proof that this is actually what we're going to see. And if we see something that doesn't follow this this trend or this theory, then it means that something about our understanding of the universe is extremely wrong. So I mentioned before that edges did kind of make a detection, but it was a detection that was very, very different from the theory shown right here. And so like lots of people in the community now are trying to determine whether or not that was a true detection or if it was like instrumental defects or etc. All right, thank you.
Okay, that's all, folks, as they say.